Okay, guys, welcome to the physics revision. In today's physics revision, we will be looking at wave motion, sound, and light. Okay, so we will combine these three topics in one. Okay, wave motion, sound, and light. Okay, so I'm not going to define what wave is, what sound is, and what light is, but maybe if we, by solving, we come across equation which asks us to define, then we are going to know what a wave is. But in short form, it's just a disturbance which travels through a medium. Like when you throw a stone in water, then there are those things that start moving on the water. Those are what we call waves. So a wave is a disturbance through a medium which transforms, which transfers energy from one point of the medium to the other. Okay, so let's begin with this question which came in 2010, wrote on 28th of October. So the question was question 8, which reads, the diagram below shows the cross section of a water wave. Okay, so this is a cross section of a water wave. When a wave is going on water like that, then they cut it, then you look into through like that. Then here they've told you this is displacement, and then this is the time here. Okay, so now they're saying the waves that the values that correctly represent the period and the frequency of this wave are shown. Okay, so where is the question now? The values that correctly represent the period and frequency of this wave are shown. Okay, so this is the question, I think. So when you have, you need to know what the period is on a wave. Okay, so on a wave like this, if you have displacement and the time here, then period becomes the time taken to make a complete wave. So period is the time taken to complete, time taken to make a complete wave. It's time taken to make a complete wave, to make a complete wave. That's what period is. Now, maybe wavelength, yeah, not wave. Let me put wavelength so that you understand. So period is the time taken to make a complete wavelength. Then, now let me explain what wavelength is. No, not a wavelength. In this case, it will not make sense. Let it just be to make a complete wave. Or, yeah, so it can be wave, or let me put it in this way, wave or oscillation, or oscillation or cycle. So this will make sense. So period is the time taken to make a complete wave or oscillation or cycle. All right. So like on this graph that we have here, this graph, this side we have displacement. Okay, so we have displacement on the vertical axis, then on the x-axis this side we have time. So this one we call it displacement time time graph. That's what we call such a graph. It's a displacement time graph. Now, when you are given displacement this side and time, we call it a displacement time graph. So, on a displacement time graph, there are about three things that we can find. One, we can find on a displacement time graph period. Okay, we can find the period, and then we can also find the amplitude. Okay, amplitude. So amplitude is just the maximum displacement. Maximum displacement okay, of a wave from the equilibrium. Okay, that's what the displacement is like. This straight line here, we consider it as the equilibrium. So displacement is if a particle is here and then it is displaced, it reaches there. Then again it comes back, it is displaced, it reaches there. So now this distance from here to there, this distance here, we call it now amplitude. From here to there, from this line to there, it becomes amplitude. Then time period I'm saying is the time taken to make a complete wave or oscillation or cycle. So a complete wave is, let's say if you start from here, then you make a circle like this, then you come here, you have made a complete wave, because if you were to cut this part, you bring it here, it will make like a circle. If I were to cut this, then I bring it here, it will make like a circle with this one up here. So now the time taken to make this complete circle is what we call period. What is the time taken to make a complete circle? That's what period is. So in this case, the time that it should take to move from here to come to here, it's a complete circle. It's a period. Or the time it takes to move from here up to here, it is also a complete circle, because if I'm to cut this part from here to here, and this part from here to here, and this part from here to here, and this part from here to here, if I join them, this part from here, and this part from here, this part from here to there, it will make a complete circle. So the time from here to here, it is also going to be considered as a period. Okay. So then, but we have also frequency. Frequency is just given by 1 over a period which is also represented by t. So in this question of ours, that's saying the values that correctly represent the period and frequency of this wave are shown. So period will be the time from here, if this is a 0 up to there. Okay, though here now they have not put any, or they have put markings, right? So from here 0 up to this point here, there's 1 here. So there's 0 quarter. Then if this is 0 quarter, here I can see this is half, this is 3/4, this is 1 and quarter, 1 and half. Here is supposed to be 1 and 3/4, then 2. Okay, here they were supposed to be 1 and 3/4. So from here to here, there's a 1 which is obstructed by this line. So the time taken from, because time is red on this part here, this is time. So this line represents time. So from here up to here, it is 1 second. So that is it, the time to move from here, come back to this same point here. Okay, we move like that, we make a complete circle. So the time from here to here, it is 1. So that time is the period. So it is either this one or this one is the answer. Then frequency. Frequency is given 1 over period. So we'll substitute. Now here we are saying it's 1. And here we have already said that period is 1. So where there's t, which is period, it's 1. If we put 1 divided by 1, it will give us 1. So frequency also is 1 here. So frequency is 1. So you discover that our answer is going to be B here. Then we come to this one. They're saying a typist uses new carbon paper under her top typing paper for making a copy of a letter. When she holds the carbon paper close to a mirror, she can read the letter. This is because the mirror Okay, so now the saying, uh, when a person is typing, okay, this is just about your intelligence to be able to expand your brain to understand this question. Is not about it. Maybe it was taught in class. These things they are not taught in class. It's just about understanding reality. They're saying a typist uses new carbon paper under her typing, her top typing paper for making a copy of a letter. So these are situations which some of us living in this era, we don't know what this is talking about, but for some they know. A carbon, there's what we call a carbon paper. Okay, a carbon paper is a paper that you put under another paper so that when you write on that paper, then the carbon will be able to trace the information from the paper on top of it and transfer it to another paper down it. So that's how a carbon actually works. In short, that's how a carbon works. So if you are not experienced with the carbon, then this question is just not going to make a lot of sense to you. Sorry, I have to say that. So that's the situation they're giving here. So here is just the matter of using someone's intelligence to interpret what is going on. So when she holds the carbon paper close to a plain mirror, she can read the letter. This is because the mirror, so the plain mirror just produces a literally inverted image, forms an image the same size as the object, forms a virtual image, forms image the same distance. So on a carbon paper, um, the carbon paper where the typist is using to write. Okay, so a typist uses new carbon paper under her top typing paper. Okay, uses a new carbon paper under her top typing paper for making a copy of a letter. Yeah, when she holds the carbon paper close to a mirror, so she's standing, then she's holding it close to a mirror. So they're saying hot mirror she can read the letter. This is because the mirror, so the mirror has produced. I think the answer is this one. It makes sense because yourself, when you look at your mirror, if you are a human being like this one here, okay, when you look at your mirror, if this is your left hand side, in reality, if you are not okay looking at the mirror, this is your left, okay, this is your left, and this is your right, left, right. But when you look at yourself in a mirror, the left looks as right and the right looks as left. Okay. So meaning that uh, the mirror turns things around. So on a carbon paper, this person is reading through the carbon paper. So the carbon paper must be able to, if you put the carbon paper down and then you put another paper on top of it, then you are writing here, okay, KLS. So this will also be produced on the carbon KLS as it is. But when you put them on the mirror, this should be like you should be able to turn them, I think, like this, if not mistaken. K, maybe L, S like that. Okay, so that's how maybe a person can see them because the mirror is going to convert them, turn them around. So if a person is able to read, she can read the letter. So I think this situation is kind of hard. So this kind of the answer maybe will not make sense. That's why I'm saying this is just about the thinking of me that can help me to produce an answer. Like this is how I'm thinking on the mirror. If my right becomes left and my left becomes right, even the letters here, I expect the mirror, if I look them through the mirror will reverse them in that order. So if it reverses them in that order, they may look like this. That's what I'm thinking. So if you want, just get a mirror and write some letters on a piece of paper. Go on the mirror, try to read them. You see what is going to happen. But the thing is, if a person is able to read them, I don't think it is because of this. Such kind of converting things, the right becomes left, left becomes right. It is what we call literally inverted. So is that the thing that can enable a person to read? I don't think so. What can make the person, I think, to read is that maybe forms an image the same size as the object. Yeah, this one, because the image on a plane mirror and the object, they have the same size. I think that can be the one that at least can enable a person to read. Otherwise, this one can confuse a person, I think. So the person cannot read properly because this can confuse them. So yes, so mhm. So I go to this other question here, which says echo sounding equipment on a ship receives sound pulses from receives sound pulses reflected from the seabed 0.03 seconds after they were sent out. If the speed of sound in seawater is 1,500 meters per second, what is the depth of water under the ship? Okay, here we need to create a situation because sometimes formulas they go. I don't memorize formulas, but I can create a situation that can help me to remember. So this is the surface of the water. Maybe on the surface of the water there's a ship or any boat here. So now this is the bed or the floor of the river. So this is water in the river. Okay. So now they're saying echo sounding equipment on a ship receives sound pulses reflected from the seabed. So this is the seabed. So it sends like sound. There's a machine here which is like a sonar. It can send sound here. It comes here. Then when it hits the bed, it is reflected back. So you find that in this same time taken here, the sound will go and come back. So you find that when we are calculating speed, we know that speed is equal to distance over time. Now you find that in the same time the sound goes down and comes back down, the distance that it travels in that, if this from here, if this has been given as the distance, now that distance should be twice. Okay, the distance should be twice. So it will be, distance will be 2 like that. Speed is going to be 2d over time. Okay. So now, because in the same time that is going to move from here to here, this distance here is actually twice. So when they say echo sounding equipment on a ship receives sound pulses from pulses reflected from the seabed 0.03 seconds after they were sent out. If the speed of sound in water is 1,500, what is the depth of water under the sea? So they want d here. D is the distance and then it becomes the depth, how deep the sea is. Or yeah, is it the sea? Yeah. So this is the depth. So make this one the subject of the formula. Okay, let me just do it here. Speed is equal to 2 times distance over time. So you say over that, so you cross multiply. So 1 times 2d, it will be like 2d equals 1 times s, it will be like, I mean s times t, it will be like st. Then you want D not 2, so you divide by 2, so that 2 can go. So D is going to be ST over 2. So here you substitute S is the speed, okay? So you put 1500 times, then T is the time, which is 0.3. So 0.03, then over 2 here. So you now multiply this, okay? Times 0.03, that one then divided by 2, which is giving us like 22.5. 22.5. So it'll be like the distance in meters. So here the answer will be A. Then we come to B. They're saying this came in 2010 on the 30th of November. So the question says figure 7.1 shows some of the components of the electromagnetic spectrum. Okay, so the electromagnetic spectrum is a band of waves, okay? Is a band of electromagnetic waves. So there are about 7 electromagnetic waves that we have under electromagnetic spectrum, like what we see in the rainbow. So there are 7. Let me see how many we have here. 1, 2, 3, 4, 5, 6, 7. Yeah, there are 7. And then these 7, they are remembered by this. I use this one which says roast, maize is very, then unusual, then you say Xmas, then gift. So here roast stands for radio waves. Then maize stands for microwaves. Then stands for infrared. Then this one here, very, stands for visible light. Then this unusual stands for ultraviolet. Very unusual, X stands for X-ray. Then gift stands for gamma ray. So this is how we remember these. If these are not given, just memorize this. Roast maize is a very unusual. Xmas gift. So you will be able to remember. So this order, when you have such an order like this, you must know that going from down, or rather going from down to up, wavelength increases. So here we have wavelength increases. But if you are going in this way, meaning wavelength decreases. Decreases. That's not how we spell decreases. Okay. Then also, what you also must understand that going this way, frequency is low, or frequency decreases. But going this way, frequency increases. Meaning that radio waves have longer wavelength, but longer wavelength. But when it comes to frequency, radio waves have lower wavelength. So they have longer wavelength, lower frequency. But here, like gamma rays, this side, gamma rays have short wavelength, but they have got high frequency. So going in that direction, frequency decreases, wavelength increases. But coming in this way, wavelength decreases while frequency increases. That's the thing you must understand from there. So now, having explained this about electromagnetic waves, you must understand some of the properties of electromagnetic waves. Electromagnetic waves, number one, they travel in vacuum. Then number two, they travel at the speed of light. Then in number three, they have the same speed. They travel at the same speed, they travel in a vacuum, and then, those are the common things about them. Then they differ in frequency and also in wavelength. So here, like question A, where they're saying what component is represented by A. So here we said this is the radio waves, this is the radio waves, microwaves, infrared, visible light. So this is radio waves, microwaves, infrared, visible light. The next one here is supposed to be ultraviolet. So here it will be ultraviolet. Then here per B, they're saying state the speed of the following components in vacuum. So both in vacuum, their speed is the same. It is 3 times 10 to the power 8 meters per second. This is their speed, okay? Then here they're saying, see, all electromagnetic waves are transverse. Then part one, they're saying, what is the meaning of the term transverse? So, okay, so transverse is the traveling of waves perpendicularly, is the vibration of waves in a perpendicular direction to the perpendicular to the direction of the travel of the wave. Okay, so what is the meaning of the term transverse? We are saying this is the perpendicular. This is the perpendicular vibration of the waves to the direction of travel of the wave. Okay, so this is the perpendicular vibration of the waves to the direction of travel of the wave here. If the wave is going like this, then the particles in the medium, they are vibrating like this. Then such a kind of a wave is known as a transverse wave. Then we move. They're saying give another example of a transverse wave, but which is not an electromagnetic wave. So an example of a transverse wave which is not an electromagnetic wave is what we call water waves. So water waves, like those that goes like this, they're transverse in nature. Okay, but water waves themselves are not electromagnetic waves because on this electromagnetic wave spectrum, water waves are not there. Then we come to the other question here, which came in 2011, wrote on the 1st of November. And this question says the diagram shows a displacement time graph. Okay, here they've named it rightly the way I told you. So the diagram shows a displacement time graph for a transverse wave. Okay, so for a transverse wave, this is a displacement time graph. Then they're saying, how long does it take to make 2.5 waves? So from here, this is one wave. Okay, we have one wave. We have made one wave. Then from here up to again here, we have made another wave. Okay, that is a complete wave. Then up to here, this is half. Okay, so this is one complete wave, another complete wave is here. Now here it's not complete from here to somewhere here. Okay, it's not a complete wave actually, it's just like half. So from here to here it's half, from here half, then complete. So from here to here is half. Now when they say how long is about time. How long is asking about the time. So what is the time taken from here to there? In short, that's what they're asking. So here we are at 0, then here we are at 2.5. So the time is 2.5 seconds. So the answer to no 2.5, 2.5. So it is here 2.5 seconds, which is there. So the answer is that. So from here to here, it is 2.5 waves. Then the time is 2.5. Then we move. Here they're saying which statement about refraction is true. When light passes from air to glass, so about there's the word called refraction. So I have to define what is refraction now for you to understand. So refraction, this one, is the bending of is the bending of a ray of light as it moves from one medium to the other. So like light, like the light which makes us to see, enables us to see things, it travels in straight line, so it can move from one media to another. What we mean is this. Let's say we have a boundary between two medium. This line, I've called it a boundary. We must, all of us, understand what a boundary is. It's a demarcation. Maybe I use that other term, demarcation. Okay? So a demarcation which can say this is another part, this is another part. So if a ray is traveling, let's say we have a demarcation, then this side we have water, then this side we have air. So let's say light is moving from air in a straight line like that. Then it meets, this is a ray of light, it meets the boundary. So if it is moving from air and water, they have different weight, or they are different, how heavy they are, they differ. Now, as in physics, that heaviness of something, we call it density or dense. we can say air, water is more dense. This water is more dense. Okay. Then we can say this air is less dense. So meaning when a ray of light like is moving from a medium like this air, it becomes a medium. This air, a medium which is less dense, then it is going into water which is more dense. This ray should bend. Okay. But if this was air, the ray will continue going straight. But if it is a different medium like water which is heavy, it will bend. So usually when a ray comes here, it means the boundary. We draw a line, a perpendicular line here like that. Such a line we call it normal. That a line we call it normal. So this is a normal line to the boundary. Now, when the ray hits here, it will bend because it is moving from one medium, which is air, to the other. Now, where does it bend? Like this or like that? So it bends like this towards the normal. It will bend towards the normal. So because it bends towards the normal, there is a condition which says when a ray of light moves from a more dense medium to a less dense medium, from a less dense medium to a more dense medium, like air less dense, water more dense, then it bends towards the normal. Okay. Now, what happens in terms of its speed? In terms of the speed slows down. That's why it bends towards the normal. So in air, the ray will have more speed. In water, the speed decreases, so it slows down. That's why it bends towards the normal. But if the ray of light is moving from this way, okay, if the ray of light, that is not what I'm trying to do. So let's say this is the same boundary, then this is air and this is water. Now, if a ray is moving like from water, more dense, then it reaches this one, we draw a normal. So this is a ray of light. So a ray of light will not bend towards the normal, but it will bend away from the normal. So the ray will go like that when it is moving from a more dense media to a less dense media. So it will bend away from the normal. So in this case, it means that the speed of light or, or of the ray increases as it moves from the less dense media to the other. Now, when the speed increases, meaning the wavelength decreases. Okay, so the wavelength must decrease because wavelength is equal to speed over frequency. So you find that frequency always increases, then the speed as well increases, but this wavelength should decrease. So when we look at the question, which statement about refraction is true? When light passes from air to glass, so from air to glass, so air to glass, then it speeds up. Yeah, so this one is correct about speeding up. It slows down, speeds up. So there are two answers. Now the wavelength, the speed increases. Now how about wavelength? Wavelength decreases. Here the same only C, frequency decreases. So this is not true. So it is the wavelength that must what happened is that here the correct answer is A, because the wavelength will decrease, but Frequency stays constant. Frequency does not change because this is still the property of frequency does not change. Okay, frequency will not change. We know the speed of sound is equal to wavelength times the frequency. So this frequency should be the constant of proportionality. So speed and wavelength are related, but the frequency becomes like the moderator here, so it stays constant. So here the answer is actually the correct answer is A. So we come to to be they're saying in order to produce a sound wave, there should be always be there should always be a drum vibration. Okay, so whenever there's sound, there must be vibration. Like me, I'm talking because the the vocal cavity on my throat is vibrating. All right, so also if you want to produce sound, you must make something to vibrate. So in order to produce sound wave, there there should always be vibrations. When we come to this, we're saying two successive crests of an approaching water wave are separated by a distance of 1.5 meters. It takes 0.2 seconds for one crest to cover the distance of 1.5. So here they're saying two successive crests. So if you have a wave, I need to explain what crests are. If this is the equilibrium and then you have a wave going like that. So this top part here is called a crest, the highest point, then the lowest point is called the trough. Then this word that I've said two successive is most like neighboring. They're saying two neighboring crests. So this is crest and this is a crest. Okay. So these are two neighboring crests. That's the language they're using. So we say that science works with the language. If you can't understand the language, then you can't answer it. That's the bad part about science again. So you have to be advanced in your language understanding. So two successful crests of an approaching water wave are separated by a distance of 1.5. So these two successful waves here, they're separated here, meaning by a distance of 1.5. Okay, meters, meaning from here up to somewhere here, the distance is 1.5 here. Okay, then they're saying it takes 0.2 seconds for one crest to cover the distance of 1.5. So it takes like this time here for this crest if the wave is going this way. So like for the crest to move from here to there to cover this distance from here to there, the time taken in that period it is covering that distance is 0.2 seconds. Then they say what speed is the at what speed is the wave traveling. So here we'll use the formula for speed. Speed is equal to distance over time. So the distance will be this distance it is covering 1.5. So you substitute it to be 1.5 divided by time, which is 0.2. So this is in meters, this is in seconds. Then you are going to divide that one. So you will get your calculator where you say 1.5 divided by 0.2. You're going to get 7.5 as your speed. So it will be like 7.5 meters per second. So here you write 7.5 meters per second. Don't forget units. Okay. Then here Um, we have another question that's saying, what is the frequency of the wave? So here we have this formula which says speed of the wave is equal to frequency times wavelength. So this speed is the same as this. So the question is asking you to find this frequency, this f here. F is what we call frequency, okay? F is frequency. Then this symbol here, lambda, is wavelength, wavelength. Then this v is velocity or speed, or speed. So that's what this means. So they're saying what is the frequency, meaning they want this f. So you make it the subject of the formula. So you divide by wavelength, also this side by wavelength. So wavelength, wavelength cancel. So that frequency now is going to be speed or velocity over wavelength. Now, you'll notice that speed is what we have found here, which is 7.5 divided by, we need wavelength. So wavelength is the distance between two successive crests. The distance between two neighboring crest is the wavelength. So in this case, the distance from this crest to the neighboring crest, this distance is the wavelength, and we were already told, so we know it is 1.5. So you put 1.5 there. So now frequency now, we'll do like this. Frequency is going to be equal to, so we are going to divide. So we'll get like 7.5. Okay, that one divided by 1.5, which will give us 5, meaning our frequency is going to be 5. Now the units of frequency are Hz, like that, H and Z. So you put 5, then H, then Z, like that. Okay, so that's what it is. So let's move to the next one. Here they're saying distinguish between the nature of water wave and sound wave. Some water waves are transverse wave, while sound wave are longitudinal wave. So you say water waves are transverse transverse waves. Then sound waves, or water wave is a. So here we are not going to say a. So we are going to say sound wave is a transverse wave. Water wave is a transverse wave. Then sound wave is a longitudinal wave. Okay. Then we move here. The same here. So this is coming from light. The same. This was written on 2011 on was written in 2011 on its 2nd of November. So they're saying a 4 centimeter high object is placed 8 centimeter from a convex lens of focal length 3 centimeters. Then they're saying draw a scale diagram to find the position and size of the image. Okay, so they're saying a 4 centimeter high object is placed 8 centimeter from a convex lens of focal length 3 centimeters. So this one, I'm going to move out of this so that I plot it well. So we are told that there is actually an object there is a 4 centimeter high 4 centimeter high object, okay, placed um 8 centimeters from a convex lens. It is placed 8 centimeters from a convex lens of focal length 3 centimeters. So what they mean is here is this. Let's say, let me just come here. Let's say we have a lens, and a lens we always represent it by a line. Let's say we have a lens here, and then somewhere here. So that line is not very thick, so I'm going to make it thick. I think here, let me make it black and make it more thick so that you'll be able to see it. So let's take this one as the lens. Okay, so this is a lens. Then we are told this is a lens. Then we need to draw a principal focus, a line that passes through the center of a lens. So this is a line. So let me give it black as well. Okay, so that line is not very dark, but let me see if I can so make it. Is this line horizontally well? Okay, so the diagram will not be horizontally well because this is not also horizontally well. So you may forgive me for that, but I'm trying my level best to do this. So let's say this is a principal focus, a line that passes through the center of the lens. Then we are told that a 4 centimeter high object is placed 8 centimeters away. So on this one, I don't have a ruler. I was going to measure a ruler. This one needed a ruler, but it's like the Microsoft took away the ruler, and I cannot use a ruler to start measuring. So this one requires that you measure from here to somewhere. So let's say from here it is 2, 4. Okay, let's say 2, 4, 6. 2, 4, 2, 4, 6, 8. I'm assuming these are 2 centimeter, 2 centimeter, 2 centimeter, 2 centimeter. Okay, because on the computer I cannot produce a ruler, it's not there. So now, so they're saying this object is placed away from here. So this is the lens, this line. So 2 centimeter, 2 centimeter, 2 centimeter, 2 centimeter. So it is placed here. Okay, so this is where it is going to be. So this object, it's a 4 centimeter high. So meaning I'll draw it here. So I'm going to give it the symbol of like that. Yeah, so this is how it's supposed to be as an object. Yeah, so it is 2, 4, 6, 8. Yeah, 8 centimeter away from the lens. Then itself, it is high. It is in height is 4 centimeters. So I'm assuming, let me get this line to sit on this line here. Yeah, so I'm assuming this is 2 centimeter, 4 centimeters. So this is how high it is, like that. Then I've thought that a convex lens of focal length 3 centimeters. So if from here to here it's 2, then on the middle there it is a 3. So what I'm going to do, I'm going to show that Okay, not that one. I'm not using that one. Let me use this one. So from here, this is 2, but 3 should be here. Okay. So that is how high it is. So maybe let me do like okay, another one here. Oh, another one will be here. Oh my God. Okay. Okay. No, no, no. So now I'm not going to use this one. This one are troubling me. Let me try to use these others. So let me try to use ink. Now, if I use ink, I should use the one which is more thick, right? Which one? Thickness. Okay. So this is where the 3 centimeters is. This is from here to 4, but on the middle it is the 0, 1, 0, 1, 2, 3, 4 here. So then here again, so it has 2 focal lengths, the convex lens. So this is F as a focal length. This one we can call it F naught. So these are 2 focal lengths, F and F prime. So now they're saying draw a scale diagram to find the position of the image. So for you to draw the position of the image, you need to draw these rays. So there's a straight layer that you draw from here that goes up to there. Okay. When you draw such a ray, let me even increase its thickness so that we see it. So a ray that we are going to draw will go like that. When it reaches the lens, then it will bend. Like this ray will bend, passes through the focal length. I mean the focal point. There, it will pass through the focal point. That's how it is. Okay. Then after it passes, that is all. Then you draw another one from the top. Again, it should pass through the center of the lens. This other rays which goes like that bends, it passes through the focal length. But another ray that you draw that should pass from here through the center of the lens. So it continues like that. Okay. So yeah. So now it has passed from the top of the object through the center of the lens. So now where the two meets, this line and this line. But before I do that, let me go to ink and then come here. Here on the rays, you need to show the arrows to show that these are the rays. So even here you show the arrow. Even here you show the arrow like that. Okay. So now where now these two meets, that's where the image is, because they're saying to find the position and size of the image. So now here you will come to notice that here that's where the image is going to be. So you draw a line from here to there like that. Okay, like that. So that's where the image is now. The image should fall should do face downwards like that. So exactly. So this is how it should be. Yeah. So this is the image. This is the drawing how it should be. Okay, so from here to here it is 8 centimeters. Okay, then from here now we don't know. So here we can approximate position of the image. So from here we'll measure from here to here. So you check that from here to here it is, we said this is 0, this was 2, this was 3, 4. So this should be 4 point. Here we said on the middle here supposed to be 5. Okay, so we can approximate to say 4.8. So here the image approximately should be 4.8 centimeters. Okay, because from here 0 to 4, then 5 should be here. This one should be like 8. Okay, 4.8. Then how? So because if I said this one here will be per 1, okay, this is 2, this is a 3, this is 4, this is 5, this is 6. So here it will be like, if you are 4, to reach per 5 you are say 4, 2, 4, 6, 2, 4, 6, 8, okay, then 5. Yeah, so this is should be 2, 2, 4, 6, 6. So it should be 8.6. 8.6. Then we move the same size of image. So here size of image can be measured again. You can use a ruler to measure from here to here, but we already determined that from here to here it's 2, from here to here it's 2. So from here to here we are going to approximate that from here to this line where it is, this is 2. But where it is exactly there, it is at 2.2 somewhere there. So come and say here it will be 2.2 centimeters. Then we'll go to the next question. This one came in 2012, which says the diagram below represent a sound wave. So this is a sound wave. Then they're saying in a space of 120 centimeters, there are 10 compressions and 10 rarefactions. What is the speed of the sound wave? Okay, so here we need to understand the language they're using. So they are what we call compressions and the rarefactions. So like if rarefactions, like compressions, are region where particles are close together. Then rarefactions are regions where the particles of the wave are not close to each other. Okay, so like in what I'm drawing here, I want to demonstrate what rarefactions and compressions are. So like in this what I'm drawing here, so these are what we call, these regions where the particles are closer, these are what we call compressions. Then these regions where particles are not very close to each other are what we call rarefactions. Okay, so now they're telling us that in a space of 120 centimeters, you find that in that space there are 10 rarefactions and 10 compressions. So in other words, we can know the wavelength by just dividing this by 10. So if we divide by 10, we can know wavelength is from one rarefactions to the other, like from one compression to another compression. That's where you find this is the wavelength. So now we need to know if we have been provided 120 centimeters, then there are 10 rare compressions and 10 rarefactions. We'll just divide it by 10 so that we know that the wavelength will be 12 like centimeters. Now, if that is 12 centimeters, which is there, so this is the wavelength. Now, even here, when you check here, the time taken to move from like this one to this one, this also becomes like the wavelength. This distance from here to there also becomes like the wavelength. So if this distance becomes like the wavelength, then the time spent from there to there must be known. So from here to there, it is 0.8. Then from there to there again, 0.08. Here it is 12. So we can know from here to, to from here to there what it is. So if we say 12 minus this, we know what it is from there. So let me just use that one to do that. So if you say 0.2, 0.12 minus 0.08, so I get 0.4. So from here to get is 0.04, even from there to there 0.04. So that is the time. So time to make one wave is like 0.04 seconds. Now the question is asking what is the speed of the sound wave. So speed is equal to distance or wavelength over time, then which is going to be distance is 12, okay, divided by 0.04. So this one now you are going to get your calculator and then say 12 divided by 0.04, which will give you like 300. So this one will be 300. So it will be like 300. So this is in centimeters. You see centimeters. This is in second. So it will be like 300 centimeters per second. So the answer will be B. Then we move to the next one, which came in the same year. The diagram shows a sound wave reflected from a brick wall. So this is incident. I think this should have been incident. So sound wave incident, like the incident. Then here sound, sound wave. So this is incident sound wave. Then this is reflected sound wave. So sound wave comes here, then it gets reflected. Then they're saying compared with the incident wave, the reflected wave has, then they're saying greater amplitude, shorter wavelength, same speed, same velocity. So here, velocity is not the same because velocity is speed in a specific direction. So this one, the speed was going like, the velocity was like going in that way. Now it has changed. So in terms of amplitude, the amplitude, I'm sure it's going to be the same. It is just going to be the same. So compared with the incident wave, the reflected wave has greater amplitude, shorter wavelength, the same speed. Yeah, they should be traveling at the same speed. Okay, so the answer should be C. Then we move to the other one here, which came in 2012, written on the 7th of November. They're saying 6 light and gamma rays are both examples of electromagnetic radiation. Then they're saying name two other types of electromagnetic radiation. So on the roast maize is very unusual Xmas gift. So if you have mentioned light and gamma rays, you are remaining with about 5. So either you can mention about radio waves, and you can mention also infrared. There are many there. They were, what are remaining are X-rays. Then what are also remaining are microwaves. Then because roast maize, that is radio waves, microwaves. Then is that is infrared, unusual ultraviolet, Xmas gift. So all those are supposed to be mentioned ultraviolet. Then they're saying state two differences between light and gamma rays. So the differences between these two, like light and gamma rays, are that these have got different frequency. So you can say number one difference is that they have different wave length. Then the number two difference is that they have, so here they're supposed to be, they have different wavelengths. So they have also different frequency. Then here they're saying the speed of light is 3 times 10 to the power 80 meters per second. Calculate the frequency of yellow light of wavelength this. So they've given you the speed, then they're asking you frequency. So here you use the formula which says speed is equal to wavelength times the frequency. So the question says calculate frequency. They want this frequency. So when we make frequency the subject of the formula, it will become like wave velocity of the wave, or speed of the wave, divided by wavelength. So you substitute here, you say equals frequency is going to be equal to, so where there's speed, you put this one 3 times 10 to the power 8, then over, okay, then where there's wavelength, you put this one 6 times 10 to the power 7. So whenever you are dividing like this one may be hard for me to use my calculator, but using my scientific calculator, it's easy to work now. Yeah, but I'm going to use mathematics here. So here to mean that we'll have like 3 divided by 6. Then since these are the same, the bases, so say, okay, the answer should be multiplied times 10. Then we subtract the powers, like 8 minus, open brackets, -7. Yeah, I think this is how we do it. Then which is going to be like this. 6 into 3, it will be like 0.5 times 10. Then this one, it will be negative, negative, positive. Then it will mean 8 plus 7, which is going to give us 15, I think. So it will be to the power 15. So then that will be the answer. Now, since we are looking for frequency is in hertz. So the answer should be 1, oh, 0.5, 0.5 times 10 to the power 15 hertz. Now, here if you want, you can remove this point here. You take it that way. So if you remove the point, it will be like 5 times 10 to the power. So if you take the point to the right, this should reduce. So it will be now to the power 14 times hertz. So either this one or this one here. Then we move. This one says our figure 7.1 shows a ray of light from air to water. The diagram is not drawn to scale, so shows a ray of light from air to water. Then they are saying here, determine angle of incidence. Okay, so the angle of incidence is this one here. The angle of incidence I is the angle between the normal and the incident ray. So this one becomes what we call the incident ray. But this one becomes the refracted ray. So the angle, this one, the angle here R is called the refracted angle of refraction. This angle between the incident ray and the normal, this angle here becomes the angle of incidence. So the angle of incidence can be found if we consider the angle between this boundary and the normal. This angle here is right angle, meaning it's 90. So the whole of this from here to here is 90. But we have been told that from this incident to this boundary is 20. So for us to know this other one, we'll say 90 minus 20. So it will be like 90 degrees minus 20 degrees is equal to 70 degrees. So this one will be the angle of incidence. So the total here is 90, but here you have only been given this. So how can you know that? It's common sense to say this other one is 90 minus 20. That will remain will be 70. Then we'll come here, angle of refraction. So angle of refraction is this one. I've told you this one here. It's the angle of refraction. So angle of refraction again from here up to somewhere here is what? Is 90. All right. So now, however, they've told us that from here up to there, it is 131. So now, for us to know this, we'll say 131 minus from here 90. What will remain up for that? So for us, we'll now say 131 degrees minus 90. Okay, so what are we going to say? So it will be like 1, then there it will be like 4. Should be 41 degrees. 131 minus 90. 19, if not mistaken. Okay, let me just confirm using my calculator. So 131 minus 90, 41. Yeah. So now here, when they say calculate the refractive index represented by the symbol like this is equal to sine of the angle of incidence over sine of the angle of refraction, which becomes equals to, here will come, here where there's incidence, we'll put this angle here, 70. So here will come, or say sine 70 degrees over, then here R will put 41. So say sine 41 degrees. Then we'll continue. So what we are going to do, we'll get our calculator. So I'm going to say 70. On my calculator, I start like 70, then I go like, I'll come like sine. So 7 sine 70, 0. Okay, I'll just do it at once so that I don't waste much time. Say open brackets, I'll say 70, then I'll go here sine, then close brackets. So I've punched this one, then I'm dividing it, divided by open brackets, this one here. I'm going to say 41, 41 sine 41, this one, close brackets. So this one divided by that, divided by this one, which is this one. Then if I say, I think this is the answer, if you're not mistaken, 0.65, but let me say equals, yeah, 1.4. So here it has given me 1.4. So this is the refractive index. It has no units, so it will be 1.4 like that. Then we move to the next one. So here they're saying figure 8.1 shows a boat which uses ultrasonic waves to calculate the depth of the sea. Okay, so this is a boat which is using ultrasonic. So it sends sound, it is transmitters, then sound is reflected, goes back to the detector. This is the seabed. Then they're saying the speed of sound, maybe let me come this side. Okay, the speed of sound in water is 1,400 meters per second, and an ultrasonic wave has a frequency of that. Then they say calculate the wavelength of the ultrasonic sound. So we know that speed is equal to wavelength times the frequency. So they want wavelengths. So wavelength is going to be equal to speed or velocity over frequency. So we divide. The speed has been given as this, and the frequency as this. So speed 1,400, frequency as the 28,000. So same here, 1,400, okay, divided by 28,000. So now we'll quickly call upon our calculator and do the division. Like 1,400 divided by 28,000, which will give us 0.05. So 0.05 will become the wavelength in meters. So 0.05 meters. Then they're saying B, The pulse takes 0.2 seconds to travel from the transmitter to the seabed and back to the detector. Calculate the distance to the seabed. So this one, it will be like speed is equal to 2d over time. So they are saying calculate the distance to the seabed. So like it took this one come here and come back. So here the distance, it traveled that distance twice. It went and it came back. So the distance it moved was twice. But if we want only the distance, then it should be once. So the formula is like this. So we want this distance. If we make it the subject of the formula, I said this will become like d is going to be v times t over 2. So which will be v is the velocity which they gave us 1400 times t, which is time they've given us 0.2, then over this time to here. So evaluate here the distance. So we are going to say 1400 times 0.2, it will be that, then divided by 2. So the distance will be 140. So 140 meters. So here you write 140 meters. Then we move. Here, this came in 2013. They're saying the figure below shows a graph of wave motion. Okay. So displacement time. So this is a displacement time graph. Then they're saying which quantities are shown by distance P and Q. So P, I told you this is displacement. So P, I mean, is amplitude. So P is amplitude, either this one or this one. No, they are not half, they are full amplitudes. Then this distance from here to here, I said it's period. So it's period. So either this one, but this one is wrong. So this one is period. This can be wavelength if this is side we had distance. Okay, distance and displacement. Then this from here becomes wavelength. Now we have displacement time, then this distance here becomes the period. So the correct answer is A. P, this one is the amplitude, then this one is the period. So we move. So this one 11 says all of the following are properties of radio wave except it causes particles of medium to vibrate perpendicular to its direction. All of the following are properties of the waves. This is a property of a radio wave because radio wave is a transverse wave. So transverse wave, they have perpendicular, they vibrate perpendicular to direction. Then it travels with a speed approximately of 3 times 10. Yeah. So the radio waves, this is the speed at which they travel in vacuum. It is undeflected by electric or magnetic field. It is undeflected by electric or magnetic field. These they don't get affected, I think, by electric or magnetic field. It does not travel in vacuum. Now these they travel in vacuum. So this is the one which is not true because the question says all of the following are properties of a radio wave except this one where it says it does not travel in vacuum. This is not true. Then we move. This came in 2013 on the 16th of October. They're saying figure 7.1 below shows an incomplete ray diagram. Then they're saying complete the ray diagram above to show the position of the image. Okay, so if this is the object, so let me do like this. So I'm going to do like this, where I'm going to draw what I told you previously, that This is how we do it. So you draw a line from here to here. Okay. Then another one should come from there, then it passes through the focal length. Okay. You have seen it. So then another one should pass through the center. So the other one should pass through the center. Okay. Don't worry, this is what we are seeing. So these rays of light are not meeting. So since they are not meeting, we try to extend from behind. That's what we do. So this one, we'll draw another ray where we'll try to extend it from going in reverse like that. Okay, so when it is going in reverse, we put it into dotted like that. It becomes dotted. Okay, so let me just make it these two lines almost the same. Yeah, but the other one dotted. Also here, you put it in reverse. Okay. What's going on now? Hmm. Now it should be dotted like that, just like this one. Hmm. Now where the two meets in reverse, after you dot them, I think this one is not lining up with the other one there. Good. So now where they meet there, that's where the image is now. So the image is this side behind here. I think that is the point at which it is. So we are going to give it that. Okay. Then we'll give it the upward or not downward arrow, upward arrow like that. You've seen? Okay. So now that's our image. So that's how you need to draw it. So we have, oh, it should squeeze this side, I think. So let me just squeeze it, this one. Somewhere there. Uh-huh. Yeah. Yeah, exactly. So this is the object. This is now the image. So these rays here, they're supposed to have those two arrows I talked about. Like here, you draw the arrow. Even here, the arrow. Even here, like that. So complete the red diagram above to show the position of the image. We have done that. Then they're saying give two characteristics of the image formed. Like this image formed here, the characteristics are that one, it is upright. So you say it is upright. And another characteristics is that it is bigger than this, so you say it is magnified. It is magnified. Then the other characteristics that we know is that it is a virtual. It's not a real image. So you can say it is virtual, meaning not real. Virtual is like this. If you want, you can say it is on the same side as the object, on the same side of the lens as the object. So we move to the next question. Came in the same year. Figure 5.1 shows a water wave traveling in a constant direction from left to right in a report tank. The time it takes to travel between x and y is 0.5 seconds. Okay, so this is a water wave traveling in a constant direction from left to right in a report tank. They're telling us the time it takes to travel between x and y is 0.5 seconds. Then they're saying calculate the frequency of the wave. So frequency of the wave, frequency f, remember I told you that it is equal to 1 over time period. Okay, this. So time period is the time taken to make a complete wave, like the time it can take to make a complete wave, like from here to there. This is one wave, one, and this is two. Okay, so that is what we call frequency. Okay, frequency also is the number of waves per second, the number of complete waves per second. So frequency by definition, this word frequency is the number of complete waves per second. So that is a frequency, what frequency is. So like in this case, I can't see this one to be a constant because from here to here it's a complete wave. So we needed to know the time there. Then from here to there also it's a complete wave. We needed to know the time. But let me see from here, maybe from here up to there, so no. So there's no uniformity in terms of how the wave is. So here we can just simply say that we will calculate the waves which are there. We have 1, 2, and then if this is 2, okay, so 1, from here is 1, then 2. Then from here up to somewhere, from here, this is as good as from here up to somewhere there. From here to there is as good as from there to there. Okay, some Yeah. So here this is quarter, and from here to here is quarter, to there it's half. So like from here to there it's half. So from here to here it's one wave, two wave. So up to somewhere here, from here to here is somehow half. So in the total number of waves here we have one, two, and half. Okay, so we have um 2.5 waves. Okay, so now it's quite a tricky question, guys. So it is involving me to think, to come up with the answer. So I need to calculate first of all. I think I need to find the speed of the wave. I'm going to use the speed is equal to wavelength times frequency. Yeah, so this is, I think, what I'm going to use. But before I use that one, I need to know this speed. Speed should be equal to distance over time. Yeah, that's what I'm going to use. So now, distance is going to be from here to here, it's 0.5. Again, from there to there, again 0.5. Okay, you have seen that this and this are the same as this and this. So here, from here to here, 0.5, from there to there, 0.5. Now this, I told you that from here to here it should be like half of this. So now it's like, oh sorry, my battery is now low. Let me just charge it a little bit. Here, from here to there is 0.5, 0.5. It will be like 1. Now from here to here it's 1. Then from there to there it will be like half of this, which is 0.25 if not mistaken. So let me just confirm. So 0.5 divided by 2 is 0.25. So from here it is 0.25. So 0.25 plus this will be 1. From here to here is 1. So plus 1 is going to be, sorry, so it is going to be 1.25. So now, so meaning that here we change to distance is from here up to there, which will be 1.25 meters, over time it will be from here to there 0.5 seconds. So this is going to give us like these questions, guys, are quite tricky. I can't lie, they need thinking. So 1.25 divided by 0.5, we are getting like 2.5. So 2.5 is the meter per second, is the speed. So now, having known the speed, so we can make frequency the subject. Wave frequency the subject of the formula. So frequency is going to be equal to speed over wavelength. So this becomes the wavelength. The distance from crest to crest is also the wavelength. So the wavelength is 0.5. So you say equals the speed we have found it, which is 2.5 divided by the wavelength, the distance from crest to crest, which is 0.25. So what are we going to get as the frequency? So let's see. So this one divided by 0.5, we are getting like 5. So it will be like 5. So the answer will be this as the frequency. Then we'll move. The next question says, state the difference between a transverse wave and longitudinal wave, giving a suitable example for each. So you're going to say in transverse, okay, this should be in transverse waves, comma, the vibration of the particles of the medium is perpendicular to the direction of travel of the wave. Then you say, wow, in longitudinal waves, comma, the vibrations of particles of the medium is parallel to the direction of travel of the wave. Then here you give examples of sound of transverse is water wave, while that of longitudinal wave is the sound wave. Yeah, so that is the answer. I just found like that somewhere. Then this one came in 2014, wrote on 6th June. A girl stands between two walls as shown in figure 6.1. She shouts once. Okay, so she shouts once. So there's a girl here that is standing in between two walls. There's wall A and wall B. Okay, so the distance from R to A is 220 meters, and then the distance of R again to B is 165 meters. Then here they're saying calculate the time interval between the first two echoes that she hears. So the time interval is the time uh, that elapses between two uh, time. So like this girl, when she shouts, her sound will move like this, comes here, and bounces back to come to her ear. Also, at the same time, the other sound can go here, bounce there, and come back to her. Now, what they want is the time difference. Time interval is time difference. So now they've told us the speed of sound is this. Okay. So now you know that this uh, sound will go like that and come back. So it will travel this distance two times for the same time we are looking for. So we know that speed is equal to, it will be like 2 distance over time. Then we are looking for time. We make time the subject of the formula. So to be time is equal to 2 times distance over speed. So here it will be like 2 times distance. In this case, it will be, we'll use 2/21 over speed we have been given as 330. Okay, so which will be equal to, we are going to find the answer here like this. So we are saying 2 times 220, it will be like 440 divided by 330 divided by 330, it will be like 1.3. So just write 1.3 seconds first as the time for this first instance, time 1. Then another time is going to be the same, 2 times now this distance 165 divided by the same speed 330. So it is going to be, this will be time 2. Okay, so we are going to say, okay, go divide 2 times 165 equals, oh, we are getting that divided by the same, it is 1. So here the time is going to be 1. Oh, look at my madness. So it will be 1 second. So now time interval, which is time change, it is going to be T1 minus T2, which will be T1 was 1.3 minus this T2, it is 1, which is 0.3 seconds. So this will be the time interval, the change in time. So that will be the answer there, guys. Then we come to this one where they're saying, this came in 2015. They're saying, which of the following describes the difference between X-rays and gamma rays? Then you're saying gamma rays and X-rays have different sources. Yeah, this one makes sense. Gamma rays travel faster than X-rays. No, they all travel at the same speed. Gamma rays have a lower wavelength than X-rays. Or longer wavelength. No, that is not true. They actually have a shorter wavelength. Then gamma rays do not affect photographic films. That is not. Gamma rays do not affect photographic fumes. No, they do affect. Radiation affect photographic films. So the correct answer is A, which says gamma rays and X-rays have different sources. Then question 10 says a report tank with a vibrator hitting the surface of water with a frequency of 60 Hz produces 10 complete waves in a distance of 15 centimeters. Then they're saying what is the velocity of the water waves produced? Okay. Mm. These questions. So mm, this is a frequency. Then the third produces 10 complete waves in a distance of um, 15 centimeters. So let's try to convert 15 centimeters into meters by dividing by 100 so that we get 0.15 meters. Okay. So now mm, there the frequency is that and the distance is that. Okay. We know speed has got wavelength times the frequency. So we have been told that there are 10 complete waves in this. So now we will know how much wavelength one wavelength is. Yeah, so here frequency we have been given is 60 Hz. Okay, now we need to know wavelength is what. So wavelength has been hidden in this. So to know a wavelength, we have 10 complete waves in 15 centimeters, which is 0.5. So for us to know one wavelength, we will divide 0.15 times divided by 10. So we'll just do likewise. So 0.15 divided by 10, which will give us 0.015. So meaning the wavelength becomes 0.015 meters. So substitute wavelength is 0.015 times frequency, which will be 60 Hz. So I'll multiply this. So like that, which is already that times 60, which will be 0.9. So the answer will be this 0.9 meters per second, which will be A. Then 11 says, when a sound wave passes through air, the particles of air oscillate. So when sound waves passes through air, the particles of sound oscillate perpendicular to the direction. No, they oscillate parallel to the direction of the wave. Yes, the answer is B. Then this one was written on 19th August 2015. So here, figure 5.1 shows the electromagnetic spectrum: gamma rays, P, ultraviolet, visible light, Q, then microwaves and the radio. 1, 2, 3, 4, 5, 6, 7. So the order has been reversed. Roast maize is very unusual Xmas gift. So roast maize is. So this one is infra. Is for infrared. Infrared. So roast maize is very unusual. X. So this is X-ray. X-ray. Now the same A state the name of component P. So here we have said this is X-ray. Then component Q. This we have said it is infrared. Then B, which kind of radiation is used to part 1 detect an aircraft? So the one they use in detection of aircraft, they use even radio waves, and also infrared. Then to treat skin cancer is treated using X-ray and gamma ray as well to some extent. Then we go to part C. Calculate the frequency of radio waves detected by an area 1.5 meters long. So assume that C, which is the speed of light, is equal to 3 times 10 to the power 8 meters per second, and the area is a quarter wavelength long. Okay, so they are saying we're calculating the frequency. So we know speed is equal to wavelength times the frequency. So we are looking for frequency. Then they've given us the speed. Then they told us that calculate the frequency. So we'll make frequency, this one the subject of the formula. Frequency is going to be speed divided by wavelength. So they've told us that calculate the frequency of radio waves detected by an area 1.5 meters long. Assume that C is equal to 3 times 10 to the power 8 meters per second, and the area is quarter wavelength long. So if the area is quarter wavelength long, it means that calculate by an area 1.5 meter long. So if it is quarter, meaning we multiply this by a quarter. So like 1.5 times 1/4 to know the actual wavelength, because the same, and the area is quarter. Oh, so the area is quarter wavelength. So meaning if this is wavelength, from there to there is wavelength. So from here to here to here. So from here to here it's quarter. Okay. From here to here is quarter, quarter, half, quarter, 3/4, quarter, 1. So they've told us that calculate the frequency of radio waves detected by an area 1.5 meter long. Now this area is 1.5 meter long, but that 1.5 meter long is quarter wavelength. So meaning it's like from here up to here, which is quarter. So what they're saying, 1.5 meters. That's what the language has. Language, guys, is really crucial. So the area is quarter wavelength. So the area of this one, the area now long is quarter wavelength. So in short, for it to be in full wavelength, you multiply by 1, 2, 3, 4. Okay. So this is by 4. So this is 1.5. Again, this is 1.5. Again, this is 1.5. So times 4. So 1.5 times 4. So you come here, you say 1.5 times 4, which will be 6. So meaning it will be equal to, here you have like 3 times 10 to the power 8 over 6. So here you can even say times 10 to the power 0, so that it becomes easy for you to do the division. So like at 6, already we found that the wavelength is equal to 6. Okay, now I'm just multiplying by 10 to power 0. In the indices, 10 to power 0 is just still equal to 1. So I haven't done anything. I'm just trying to use this one so that I say 3 divided by 6, then times 10 to the power 8 minus 0. So I'll get the same base, then subtract the powers. So that I'll say 3 into 6 into 3, 0.5, then times 10, then 8 minus 0, 8. So it has become easy for me. So this one I can even move this one further. So it will be like 5 times 10 to the power 7 hertz. So that should be the frequency. So it can be 5 times 10 to the power 7 hertz. Then we move to the next one. A fishing boat on Lake Tanganyika uses ultrasound of frequency 6.0 times 10 to the power 14 hertz to detect fish directly below. 2 echoes of the sound are received, one after 0.05. 2 echoes of the sound are received, one after 0.09 seconds coming from a shore or fish, and the other after 0.12 seconds coming from the lake bed. If the lake bed is 8 meters, 84 meters below the sound transmitter and receiver, calculate the speed of the sound waves in water. This is quite crucial, guys. So we have a fishing boat. So let's have, this is the surface of the water. This is a fishing boat. Then they're saying on Lake Tanganyika uses ultrasound of frequency that to detect fish directly below. 2 echoes of sound waves are received, one after 0.09 seconds coming from a shore fish. So there's some fish here. Then there's, after an ultrasound is sent, then it is heard after the time of 0.09 seconds. Then the same, and the other after 0.12 seconds from coming from the lake bed. So if this is the lake bed, then the other one is detected later. Okay, so the other one went and then gets detected later. Then the time which elapses is 0.12 seconds. Then they're saying if the lake bed is 8.4 meters below the sound transmitter, so the lake bed is 84 meters below. So meaning here the distance is, they've told us that it is 84 meters below the transmitter. Calculate the speed of the sound waves in water. So we need to calculate the speed of sound wave in water. So speed is equal to 2 times distance over time. Now, what are we going to use to find the speed? Because we have been provided this value and this. So the one that we are going to use to know the speed of sound in water is this formula and this distance. Distance that provided as it is 84 meters. Then the time we should use is this, which it took for the wave to go down and come back. This one is 0.12, not this one which came from the fish. No, this one which came from the seabed. So the time is going to be 0.12. So meaning we are going to say equals 2 times this distance 84 over this time 0.12. Let's see. So we are going to get this 2 times 84 equals then divided by 0.12, which is I think it makes sense. Yeah, 1400 meters per second. Yeah, because the speed of sound in air is like 340 meters per second. Now in water, speed of sound is faster. So this 1400 makes sense. Okay, so here it's 1400 meters per second. Then here they say the wavelength of sound waves in water. So we'll use the same formula. This is equal to wavelength and the frequency. So we need wavelength. So wavelength is equal to speed over frequency. So speed we have found to be 1400 divided by frequency. It was already provided, this one here, 6.0 times 10 to the power 14. So this one it is 6.0 times 10 to the power 14. So what I'm going to do here is also to say 14. Okay, I'll move a point here, 1, 2, 3. So 14 point. Because I'm having trouble my calculator dividing powers. So I'll move a point here, 1, 2, 3. So to be 1.4 times 10 to the power 3 over this one, like 6.0 times 10 to the power 14. So that this one I make it easy for myself, 1.4 divided by 6.0 times 10. Then I'll get 3 minus 14. 3 minus 14, which is going to be equal to, yeah, this one would be simple for me, I think. Then it is going to be like 1.4 divided by 6. So it's like I'm getting 2.3. So I get 0.23, 0.23 times 10. Then 3 minus 14, 11. So it will be like negative 11. So now that one, I can even move this one 1, okay, 2. So I can even put 1, move this point here 1, 2, meaning this one I'll subtract 2. So it will be like, the answer will be like 2 point, okay, I'll just subtract 1. Let me put 2.3 times 10 to the power. I'll just subtract 1, so it will be negative 10 meters, I think. So 2.3 times 10 to the power negative 10 meters as the wavelength. Then they're saying, see the depth of the shore if the depth of the shore of fish below the boat. So we need the depth here of the fish below the boat, this distance from here. So we use the same formula, which is the velocity is equal to 2d over time. So we'll make d the subject of the formula. So d is going to be equal to v times t over 2. So velocity, we have already found velocity of speed, so the speed of sound in air, which is 1,400 times time. We'll use this time here, 0.09, the time which it took for the wave to come from the fish. So which will be 0.09 divided by 2. So that we'll use the calculator quickly, where now we are going to say, okay, this time around we are going to say 1,400 times 0.09 because then divided by 2. So the depth there, it makes sense, it will be 63 meters. So this one will be 63 meters. So this one was 84 as they gave us themselves, but this one 63, which makes sense. So this one was written in 2016. Let me see how long the video is. 2 hours 25. So let it go to 30. Then I stop so that we will finish it. Otherwise the video shouldn't be very long. So this one says it was discovered that 120 crests passed through a slit in 2 hours. What is the frequency of this wave? So now you have 120 crest in 2 hours. So now if these are crests that are passing in 2 hours, we need to know, the question is saying what is the frequency. So like we know that 120 crests 120 crests, it means these are complete waves. So these are complete waves. So this time, which is 2 hours, let's convert it into seconds so that it can make sense, guys. So these 2 hours in 2 seconds, we will say if you are on hour, you move to minutes, then you move to seconds. So if you are moving from hour to minutes, you multiply by 60. Then again from minutes to that, you multiply by 60. So here you have 2 hours. So 60. Let me convert first into seconds. So 1 hour is equal to 60 minutes. What about 2 hours? Is equal to x. So you have x is equal to 120 minutes. Good. So 1 minute is equal to 60 seconds. 120 minutes is equal to x. Okay. So your 1 minute, 120 minutes, you have x, so that x is equal to, so mm, 120 times 60, 7,200. So it will be 7,200 seconds. So now what that is that here you divide this by 120 crests, so that we understand what it is going to be. So because what we are looking at is the frequency. Frequency is the number of complete waves in a second. Now these crests, we take them as waves. So, and this is the total time now provided. So total time divided by 120. So like that, we divide by 120 to know the frequency. So if we divide it by 120, it should be 60. So the answer should be that. This question, guys, hey, they are quite tricky, because crests, as I already explained, they are these, like if a wave is going like this, they are like, so these are crests. This one, this one, this one, they are crests. So from here to here, it's a one wave. So count one wave, two wave, three wave, four wave, five waves. So if there are 120 crests, meaning we are considering that there are about 120 waves, then in 1 hour. So then when they are asking for frequency, they are saying frequency is the number of full complete waves in 1 second. Okay. So in 1 second, you have a one complete wave. Okay. If we say 1 second gives us one complete wave. No, it's just the number of waves, not this relationship I'm giving you to give us a wrong answer. So like the number of waves in 1 second is what we call frequency. Now here they've given us 2 hours. The waves that are passing through a slit for 2 hours, 120 crests. So now what is the frequency? So we get that total amount, which is 2,700 seconds, 7,200 seconds divided by 120, which gives us 60. Then 11, they are saying, which type of electromagnetic radiation has the longest wavelength? It is radio waves. I already explained this. 12 says, which of the following correctly gives the properties of the sound waves? So sound waves, these ones here, they are longitudinal. Then speed in air, I mentioned this one recently, upper. Let me see if it has not even gone. This one, we've even mentioned this one. So which of the following correctly gives the properties of the sound waves? The nature of the sound wave, it's longitudinal. The speed of sound wave in air is 340. So the correct answer is A. Okay, so we are now per 30. Let me see the slides which are remaining. We are at 29 of 100 slides. So tomorrow we are going to push more slides. If I'm going to knock off very early from work, because knocked off late today because of certain works I was doing. So yeah, so for today, let's end here, guys. We pray all things go well. We complete these things. As for now, bye and see you in the next revision.